Oh, there's one. Michael. Okay, I think I've got most of you at least. Let's see if we can get one note going. Okay, this is from okay, I assume you can see the tablet here that I write on.
Yes.
And I think we're ready to go now. Let me see if I can summarize some of what we've been doing. So we're in section 1.6, and so let's just 1.6 has a lot of stuff in it, by the way. We're not going to do 1.7, so that's makes it easier, and maybe I'll be able to turn the quarter on 1.6 today and start some of the stuff in the next chapter. That's what I'm hoping. But let's talk about what's on page 50, because that's a nice summary. So if you have your book, turn to page 50 in section 1.6. And there's a paragraph there which I think is attempting to summarize what they've done up until that point. So let me just read from that and look at the Venn diagram. The second paragraph it's the third paragraph on page 150 says, a basis for a vector space is a linearly independent subset of V that generates V. Okay, so that sentence is simply the definition of a basis. It's a collection of vectors that are linearly independent and generate all the vectors in V. If V has a finite basis, then every basis for V contains the same number of vectors. That's a theorem that they prove in a section. But here, instead of giving the proof, they're just telling you it is a fact. So if you have two bases in a finite dimensional vector space, and they both have the same number of elements in it. The number is called the dimension of V, and it's said to be finite dimensional. There turns out to be infinite dimensional vector spaces, and those are covered more in section 1.7. And we're not going to see them that much in this class, so I'm foregoing that. Generally, a section that's got an asterisk next to it is an optional section. So we're not going to be talking about infinite vector spaces, though they do come up, and they're not, I don't want you to get the feeling like they're just highly unusual. They're just not really what we're studying in this class so much. Thus, if the dimension of V is n, every basis for V contains exactly n vectors. Well, I already said that, but that's in this paragraph as well. Next sentence. Moreover, every linear independent subset of V contains no more than n vectors and can be extended to a basis by including appropriately chosen vectors. Okay, that sentence perhaps deserves a little more attention. So it's saying that in a finite dimensional vector space. And let's assume that the V, let's assume that the dimension of V, which is the number of elements in the basis, is equal to n. So in such a finite dimensional space, with the assumption that the dimension of V is equal to n, they then say every linearly independent subset of V contains no more than. So that's worth noting. Every linearly independent subset S of V contains no more than n vectors. So, for example, if you're in R5, well, actually, let me tie this to a problem maybe. Yeah, look at problem 8. Problem 8, which we haven't done yet, but we're going to assign it later today on page 55. So if you look at that problem, they give you 8 vectors. They give you U1, U2, all the way up to U8. And these are all vectors in R5. And what they ask you to do then, well, they tell you that these vectors generate W. So if you put them all together, call this a set S, linear combinations of this S generates the whole space. But the whole space is 5-dimensional because we're in R5. So what this previous statement says is these vectors have to be linearly dependent. If you have more vectors in a set than the dimension of the vector space, then S has to be, S is a linearly dependent set. They're not linearly independent. So if you have more vectors than the dimension of the space you're in, then these must be linearly dependent, which means you could do what? You could actually reduce the collection of S to be fewer sets until you get a linearly independent set. And so that's what they're saying here, back on page 50. Every linearly independent set contains no more vectors. And they're actually saying two things. So two things that they're saying is you can reduce S to a linearly independent set. Now, it's possible It's not the case in this case, but suppose, so here's a crazy example. Suppose S in R5 just look like 1 and all zeros. Okay, that's a vector in R5. And suppose the second vector was 2 and all zeros. And suppose the third vector, this is not the case in the problem that I referred to, but this is sort of an easier thing to think about. Suppose you had 8 vectors that all look like this. Well, it's pretty clear that the second vector is just twice the first, and the third vector would be 3 times the first, and the last vector would be 8 times the first. So these are linearly dependent. And you can see that this could be reduced to what? Just the first one, for instance, if you want. So this is a linearly dependent collection of vectors in R5. And if you want to, you could reduce it to a smaller collection. Now, if the collection spans all of R5, which is what's going on in the problem that I mentioned up here, then you should be able to reduce S to a subset of itself so that all the vectors left are independent and yet they still span. In other words, you could reduce S to a basis. This is not a case where you can reduce S to a basis. These vectors are linearly dependent, but they don't span R5 because they're all simply a constant multiple of this guy. But if you also knew that S generated the whole space, then you can reduce this to a basis. That's what they're saying. Let's see. Also, here's the last comment. Each generating set for V contains at least n vectors. And I pretty much already said that. Then the last thing they say is this Venn diagram, which is worth looking at. So the Venn diagram that they have there looks like this. I should have drawn it with a bigger intersection so I can label it better. So if you're looking at sets in the vector space, there are those sets that are linearly independent. Independent sets. And there are those sets that actually generate the whole vector space. And then there are sets that do both, that are linearly independent and generate the whole vector space. And if you're in there, let me see if yeah, then you're a base. These are different bases. So again, you're looking at the intersection of these two properties in order to form a base. And if you have a set of vectors, suppose you had 3 independent vectors in R5, you can find 2 other vectors to add to that collection to form a basis. On the other hand, if you had a collection of vectors that generate V, but they're not all linearly independent, you can reduce that collection to form a basis. So you can go up or down depending on where you're at. That's a summary. Let me see if they're done with that. More or less, that's what they have to say. Any questions on the summary? If you're not clear about any aspect of what I just said, this would be a good time to say, could you repeat or could you clarify, whatever it might be. I like this part of the section because instead of just theorem, proof, this is trying to give you an overview. Okay, so let me use this opportunity here to give you a few more homework problems. In section 1.6 here, we've already had some. So let's go back and see what the homework has been. So I think the homework, let me just look at it. I could go back and pick it off, but I think you can tell me as well. I think so far we've done 1 through 5. Is that right? In this section? So in section 6, 1.6, I think we've assigned 1 through 5. It doesn't mean we've talked about them all, but I think that's what the assignment has been. If I'm not corrected, I'll just assume that's the case. And then I want to tack on a few more. So here's a few more. Go up to 9. So tack on 6 through 9. And since we are talking homework here, are there any questions about 1 through 5? I don't mind doing or talking about part of this if that would be helpful.
Should we do problem 4 from the homework?
Sure, I've got a request for 4. I think there was another person asking maybe another question. So if there was a different request, please ask. And maybe it's the same one. Okay. So let's look at 4. So 4 says, do the polynomials, and they give 3 polynomials. Do they generate P3? Justify your answer. All right. So this is, it's not the usual vector space like R4 or something, but it's the polynomial space. So in this setting, we're looking at P3 polynomials of degree 3. With the real numbers as coefficients. And you're given x cubed minus 2x squared plus 1. And you're given 4x squared minus x plus 3. And the last one you're given is 3x minus 2. So those are all polynomials of degree 3 or less. So that's what, you can get polynomials of less degree. So what is this? This is things that look like ax to the third plus bx squared plus cx plus d, where a, b, c, or d are all real numbers. Okay, so you're given these 3 polynomials, and you're asked, do they generate P3? Justify your answer. My answer is no. Okay, and there's different ways to justify it. If they did generate P3, then I would have half the conditions of a basis, right? Then if this generated P3, then I would know that this could be a basis. But we also know that what's the dimension of this? The dimension of P3 is equal to 4. And a normal basis in here normal means sort of the standard or usual one, would this be x cubed, x squared, x, and just a number, maybe a number like 1. So it's fairly clear that this is a basis. If you can generate any of these guys, just multiplying this by A, this by B, this by C, and this by D, and adding it up. So this does generate the whole space, and it's not hard to show that these are linearly independent. So P34 has dimension 4, and if this generated the whole space, well, then we have a contradiction, because we have a basis basically. If something is a basis, if they're what, independent, linearly independent, linearly independent and generate the whole space. If this generated the whole space, if they were not linearly independent, then you can reduce it and get a smaller set, which is linearly independent. So you would be able to find a subset of this, which is a basis, but that can't be, because any subset of this will have fewer than 4 elements. It'll either have 3, 2, or 1, which is, none of them are possible. So if this generated the whole space, what I'm arguing is there would be a basis of dimension 3 or less, and that contradicts this. We already have a result that all bases in a finite dimensional space have the same number of vectors. So that's the quick answer. The quick answer is, if this actually generated the whole space, then you can find a basis of less than 4 items, and that can't happen. That's from the proofs, and that's from the theorems. Now, there's a longer answer. The longer answer would be what? Let me see. So a longer answer might be to come up with to actually show to actually show they can't generate it. Why don't we, so let's try to do that, which would not depend on the theorems, which would depend on just going from the definition. So an alternate approach would be using the definition. So that would mean we'd like to show that these do not generate the whole space. So we're trying to show that if you took A1 times the first one, plus A2 times the second one, plus A3 times the last vector, or last polynomial, that you can't get everything in here. That this does not give us everything. Does not give us, and it's understood here, A1 and A2 and A3 are what? Real numbers. Does not give us all polynomials in where P 3 R. Okay, so this would be not using the theorems particularly. With the theorems, we already know the answer is no, but we would try to show that this does not generate. Now, one way to do that is, there's 2 ways to do this. One way is just to do sort of guess and check. Can you figure out a polynomial that you can't get out of this linear combination? By the way, let's see. Yeah, so it looks like well, I'm trying to guess what that might be. Because, well, could you get a constant out of this? Yeah, so let me just, this is sort of educated guess and check, but let's try it, guess and check. If this is going to generate everything in here, there must be a way there must be a way to come up with the constant one, right? Okay, if you're going to come up with a constant one, then what would have to be true? The constant term from here, which would be A1, and the constant term from here, which apparently is 3A2, would have to be equal to the constant term here, which is what? Minus 2A3. So this equation would have to be true. And what else would have to be true? Well, all the other ones, you'd have to have minus 2. Let's do the linear terms first of all. The linear term, there is no linear term in here. There's no x, but there is in here. So it would be minus A2 minus A2x would have to be equal to what? The linear term here, which is 3A3. And that would have to be equal to 0. Why? Because there's no linear term here. There's no term of x. Okay, so that would have to be true. The square terms would have to be 0 as well, right? Minus 2x, minus 2a, minus 2. No, I don't need the power here, sorry, I don't need this. Let's make sure I did that right. No linear term for A1 minus A2 is right, plus 3A3, the rest is okay. The square term would be minus 2A1 from this. Here, the square term here is A2. And there is no square term here. So you would have to get this equation would have to be true as well. And what's the last equation that would have to be true? The cubic. So the cubic equation would give you what? 1 would have to be, sorry, 0 would have to be what? Would have to be A1. There's no cubic here and there's no cubic here. Okay. So if I thought I could come up with the number 1 by doing a linear combination, these equations would have to hold. Now let's see if we get into trouble this way. This says A1 is 0. And if A1 is 0, that implies A2 is 0. And if A2 is 0 from this equation, that implies A3 is 0. So the only way you can get 1 out of a linear combination of these 3 vectors is for all of these to be 0. But if these are all 0, then you get a contradiction here. This leads to what? 1 equals 0, which is not true. So we're done. So in this case, my guesswork was sort of a good guess. Why? Because I didn't see immediately how I can get a constant 1, which is a polynomial, sort of a degenerate one. It doesn't have any x's in it, it just has the constant 1. I couldn't see it immediately how I could take a linear combination of these things and get 1. And so when I tried to see what that would mean in terms of the coefficients, it seems to mean all of these and this little progression of if A1 is 0, then A2 is 0 from here. And if A2 is 0, then A3 is 0. And that means they're all 0. And if they're all 0, then you get 1 equals 0, which is a contradiction. So that shows what? It shows that you can't generate all the polynomials in P3R using these three. Does that make some sense? That would be a way to do it directly from definition. So now we have two extremes. We have using the theory that's saying if this generated the whole space, then you'd sort of end up with a basis less than 4, which can't be. That's what the theory is telling us, the theorems. On the other hand, here's an example of something you can't generate. Now, somewhere in between, you could try to show that any polynomial of degree 3 or less cannot be generated by these things. So I just made a lucky guess, a good guess here. But you could put on the left side, you can put any polynomial, then you'd end up with what? I'm still making sure that this is all right. Yeah, then you'd end up with 4 equations and 3 unknowns, and you'd have to reduce it down to show that you can't always solve it. Okay. So I think we're in a position. There's one more thing to do in 1.6 to talk about that we haven't talked about at all. There are some theorems we proved and some theorems we just stated, and that's okay. So let me put out the agenda for the rest of today. So for the rest, we will talk about subspaces a little bit, which is a topic in 1.6 that we haven't covered yet. And then we will move into 1.7. I'm sorry, 2.1. We're skipping 1.7. But before, I should bring up the topic of exam 1. Well, why? Because we're in the middle of week 4. So let's put a little calendar on the board. Where are we? We're in February. We're on Wednesday. We're on Wednesday the 16th. So Monday was Valentine's Day. Monday, Wednesday, Friday is when we meet. So this is week 4. This is the 4th week. Next week would be the 21st, the 23rd, and the 25th. And the following week, that's the 5th week. And the following week to that would be what? The 28th, the 2nd, and the 4th. That would be the 6th week. Okay, so that's the calendar. I more or less told you we'd have our first exam in the 5th or 6th week. And we are here right now. So what I would like to do is have it in the 6th week. And does anyone know? I'm assuming none of those are holidays, at least that I know of. I think we skipped over all presidents' birthdays and things like that. So I don't think there's any official Cal Poly holiday. If I'm wrong, please speak up and let me know. But I think they're all okay.
I don't think there is.
Yeah, my personal preference would be for the 4th. That would give you 2 weeks and a couple days from today to get ready for this thing. That should give me time to give you some kind of sample test and time to have problem sessions to go over them. So that's my personal preference. But I did tell you that I probably would let you decide. And so I think that's what I'd like to do right now. Is there anyone who wants to make a pitch for one of these days other than the other? You know, is there some? You know,
It looks like the chat is going heavy for the 4th as well.
it is okay. Thank you. I wasn't looking at that. But if somebody wants to get on a soapbox and tell me why the fourth isn't good and the others are better, here's your opportunity to say it verbally. And it may come down to just maybe you have all your other midterms on the fourth, you know, it could be something as personal as that. So this could be one more midterm of a popular day to pick for midterms. Of course, those kind of arguments cut both ways. For everyone who has a lot of midterms on the fourth, there might be others who have midterms on other days too. If there's no one who wants to talk about this at all, then let's see if we can do sort of an informal poll and nail it down. So what I would do, I'm going to share the whole screen so I can see you all and ask you which day you prefer. If you don't care, I would say don't vote. If it doesn't really matter to you which day it is, let the people decide who do care about this. On the other hand, if you do care, just vote for one. It doesn't make much sense to vote for more than one day. Okay, so why don't we see if we can nail it down? So let me unshare this for the moment. Stop sharing. Yeah. So how many would prefer to have our first exam Monday, the 28th? If you do feel that way, gesture in some sense. You can thumbs up or clap or something. So I've got two people preferring that Monday.
Hey, Professor, I have a quick question.
Sure, Raymond.
So is it possible for both sections to vote on like different test days and we could go to either one if we wanted to?
I'd rather avoid that. In
Okay.
fact, I really want them on the same day, to be honest. Then you can still pick your time on the same day. But yeah, I don't, because when I have them on either day, then I got all the people who say, oh, gee, I thought I was ready, but I'm not. So can I take it on a later? And it's sort of chaotic, to be honest. And from a convenience point of view, for me, I'd rather have them both on the same day, whatever it is. But good question. Let's go on. I had a couple votes for Monday. How many prefer Wednesday, the 2nd, I believe? So for that, we've got one. Okay, so it looks like this is going to be a landslide for the 4th, but let's just see the votes. I guess you could all abstain, but by the way, we have to have the test, even if you all abstain. How many prefer to have it Friday the 4th? Yeah, it looks like it's double figures. Yeah, so I think we've got a date. Thank you very much. It's rather one-sided. I hope the other class does it the same day. I think they will, but who knows? So let me well, what do I want to do? No, I don't want to do that. That's for sure. No. Okay. What I really want to do is just go back to this. Okay. So, all right. So we have a date. Exam 1 is Friday, March 4th. Okay. What will the material be? Well, clearly all of chapter 1 that we've covered, and maybe a section or two of section of chapter 2. I hope to get to that a little bit today. So thank you for that. If there's any friend or any my classmate here who's not here, and it would be nice if you shared the news and let them know that we have a test date. Okay. I'll talk more about problem sessions maybe next time, maybe on Friday. Let's see what else we can do in 1.4. Well, the other topic that we haven't gotten to is subspaces. So let's turn to that. I'm not saying we've done everything else, but I'm saying at least we've touched upon things. But subspaces, I don't think I've talked about it at all. So there's a theorem 111, which is worth stating. It's on page 50 again, which is where that summary was, page 50. Let W be a subspace of a finite dimensional vector space V. So let W be a subspace of a finite dimensional vector space V. So W is certainly a subset of V, but it's more than that. It's a subspace itself. Remember, we've covered that before. It means it's a vector space in its own right, but everything within W is also a vector in V. So let W be such a subspace. Then W is finite dimensional. So here's the conclusions. Then W is finite dimensional. And the dimension of W is less than or equal to the dimension of V. I think that's somewhat intuitive. Moreover, if the dimensions are equal, so there's a tagline. Moreover, if the dimensions are equal, then the subspace is actually the whole space. Okay, I think, well, I really don't want to get into the proof by itself, but I will talk a little bit about why this is true. First of all, since W is a subset of V, and W is a vector space by itself, it would only make sense that the dimension of W would be no bigger than V, because every linear combination of this would also have to be in V. So this is a subspace in here. And if you think of the dimension has to do with the number of elements in the basis. So if this were not the case, there would be more elements in the basis of W than there are in the basis of V. And that's not intuitive at all, because if there were more, every linear combination of vectors of W is a linear combination of vectors in V. So that means you can write that in terms of the basis. And so it's not, it's quite reasonable to say that this cannot be bigger than that, because if it were, it would essentially be saying that the subspace contains something in it that the original space did not. That's not a proof, but it is an argument to make you try to understand and believe the result at least. The moreover part says that if the dimension's the same, then the subspace and the vector space are the same. And that makes sense, because if you had a basis in here, and then you have a basis in here, any basis has the same properties. They have the same number of elements as each other, and they generate the whole space. So basically, since they generate the whole space and And the basis could be the same for both of them because they have the same number of elements. That means everything in V would be generated by the basis in W, and that means they're the same space. So that's a quick intuitive proof of why that's so as well. Now, let's do a couple of examples to make sure we're okay on this stuff. Let's look at example 18 on page 51. So on example 18 on page 51 is the following. It says, suppose, well, they're doing F5. I'll do R5. So suppose W, I'm modifying this just slightly, is the set of 5 tuples, A1 up to A5, A1, A2, A3, A4, and A5. So these are 5 tuples, and from what I just said, for me, they're in R5. I'm using real numbers for their entries. But then they have an additional property. The additional property is if you add A1 to A3 to A5, you get 0. So there are 5 tuples in A5 and 5 tuples in R5 such that A1, A3, and A5 added up to 0. But there's more. And A2 and A4 are the same. A2 and A4 are the same. Okay. So it is now, what did they say? It is easily shown that W is a subspace of R5. So the conclusions are, so if W is written this way, then W is a subspace of R5. And I'm telling you a little more, the dimension of W is 3. Okay. The business about showing that W is a subspace, I'm sure you can do from what we did before. In other words, to show something as a subspace, there are 3 properties, right? So let me just sort of talk through that quickly. One property of being a subspace is that the 0 vector is in there. And if you have all zeros, it certainly satisfies both of these properties. So the 0 vector is in here. The 0 vector is an element of W. Moreover, if you have 2 5 tuples that satisfy these properties, then the vector addition also satisfies those properties. So it's closed under vector addition. Not only that, if you were to scale and multiply this by something, you'll get a new vector that still satisfies the same 2 properties. So what I'm saying is showing that W is a subspace is an old story that we know how to do from earlier in the book. So that part I'll just check off. It's the dimension part that is rather new. And so they're saying the dimension of W is 3. Now, what does that mean? That means there's a basis of 3 vectors that would generate, it would be linearly independent and would generate all of W. Now, that may not, I don't think that's so obvious, but then if we look at the book, they help. And the help they give is they actually show you what the basis is. So they tell you what? They tell you that -1, 0, 1, 0, 0, and -1, 3 zeros. in 1. And then finally 0, 1, 0, 1, 0. Throw those 3 vectors from R5 into a set, and they tell you this is a basis. Well, as soon as you believe that, if this is a basis for W, there's 3 vectors in here, and that means the dimension of W is 3. So what do you need just to verify? Their statement that this is a basis. So you would have to show that these are what? Linearly independent. And you would have to show that they generate this subspace. Let's do maybe the harder one. So if you wanted to show that they generate that subspace, we would have to show that any vector, let's see. Yeah, I think it's somewhat easy. So yeah, just going from definition, we'd have to show that something in here satisfying these 2 properties can be written as, you can generate all of those by doing something times this plus something times this plus something times this. Okay, so maybe I shouldn't call them A's, maybe I should call them B's. So B1 plus B2 plus B3 ends up being a vector that satisfies these properties, because this is what? This is the span of these 3 vectors. So, all right, if you were to add these up, what would you get? In the first component, you would have minus B1 from this, and then minus B2, and then 0, because B3 times that would be that. And then the second component, you'd have 0 times this, 0 times that, and you would just have B3. And in the third component, you'd have B1 from the first one, nothing from here, and nothing from here. Now let's make sure I'm doing that right. B1, yes, nothing and nothing. And what would the fourth component give you? 0 from here, 0 from here, and just B3. And then the last one, 0 from here, B2 from this one, and nothing from here. Okay, so that's what this would be. What we have to check is that what comes out of this actually is a vector that lives up all to these conditions. So we'd have to check, does what? If you add this to that, do you get 0? And you do. Minus B1 minus B2 plus B1 plus B2. So that means this condition is met. And then the other question is A2 and A4 the same? And they are. This is equal to the same as this. Okay, so what did I just establish? I just showed that any vector that would be a linear combination of this is still in W, which means what? This generates all the vectors in W. The only other thing to show, and I'll let you think about that, is that these are what? Linearly independent. If they're linearly independent and they generate W, then it's a basis of W. So that's the kind of thing they didn't ask you to do, but you should do, okay? Because they're declaring this to be a basis. So you need to check that this thing spans W and that they're linearly independent. Questions on example 18. They get a little more interesting. And I have to decide. I guess I'm sticking with the examples here. Let me go to example 20. Just because we haven't explained any of these before. Example 20. I'll skip 19. So 20 says, we saw in section 1.3 that the symmetric matrices of n is a subspace of n cross nf. So let me just do this. For sake of time, let me do it for matrices that are 3 by 3 with real coefficients. Okay, so what do matrices like that look like? Well, they look like this: A11, A12, A13, A21, A22, A23, A31, A32, A33. Try it again. 3-1. No, I guess that's right. All right. So that's our matrix notation. But if they're going to be symmetric, then that meant that this guy here is equal to this guy. And this one here is equal to this one. And put a triangle around this, and those are equal to those. So these entries are equal, the circled ones are the same, and A31 and A13 are the same. So what are we looking at? Symmetric matrices. Look like, let's see if we can draw it in a different way. So why don't we call this just A, and call this entry B, and this one C. Then this one would have to be, from what I just said, would have to be B. This could be D, could be something different entirely. But this one would be the same as that, so it would be E. This one is the same as that, so it would be C. And these are the same, so this would be E. And this would be maybe F. So if I got away from the subscript notation, but I'm trying to say again, the circled ones are the same, so these are both B. The ones in squares are the same, so these are both C. And these are the same, so those are both E. So I'm looking at not all matrices, which is in here, but this would be called the symmetric matrices. They look like this, okay? Another way to say it is if you reversed Aij is what? Aji. If you reverse the rows for the columns, then you would be going from here to here, and they're the same. So basically, if you were to look at the diagonal as this, and you flipped the entries over the diagonals, so this went where this was, this went where this was, and this went where this was, you don't get anything new. You get the original matrix back. And so that's a way to visualize it geometrically, and this is a way to visualize it in terms of the subscript notation. Okay, so that's what we're looking at. Well, not quite. I'm just doing symmetric matrices of 3 cross 3, 3 cross 3. They're looking at it n cross n, but it's the same idea. And you can use this to be your definition of symmetric matrices there. Okay, now what are they saying? In example 20, they're saying we already saw in the past that this is a subspace. I don't remember right now whether we all already saw it. I think we may have seen it. But it's not hard to show because if you take matrices, let's just stick with the 3x3 because it's easier to visualize. What do you have to show? You'd have to show that if you're looking at symmetric matrices, you'd have to show that the zero matrix is in there. Well, it is because it has this property. And you'd have to show that if you add two symmetric matrices together, then you'll get another symmetric matrix. But that will hold because if these entries are the same for each of them, when you add things, they stay the same. And then finally, if you scalar multiply this by any alpha, you still have these places where they're equal. They would still remain the same even if you scalar multiply. So it's not hard to recall or check that these are still, that symmetric matrices are a subspace. They're a subspace of this. Now, did they give us a notation for that back then? I don't know. I don't think so. But where they want to go with this is, okay, so let's call symmetric matrices, the set of symmetric matrices, symmetric 3x3 matrices to be more precise. Let's call that W. W is a subset of this thing. And not only is it a subset, all that's saying is a symmetric matrix is in the collection of all matrices. That's certainly true. And we've just verified or ran through the properties that W is a subspace. So the next question, what they're asking now is, what is the basis? What is the basis of W? Or another way, they ask the question, what is the dimension of W? Well, if you look at it like this, you could think of this as a vector. If you want to string this out instead of write it the way it looks like A, B, C, B, D, E, and again, C, E, F. So if you wanted to, you can change this into a vector that has 9 components. And it has those kind of entries. And if you were asked, what would be, if you were in R9, vectors that look like this, what would be the dimension of something like this? And I think it's pretty clear what you could do is if you set A equal to 1 and made everything else 0, you would have this. Hopefully I have 9 things there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, good. Or you can set B equal to 1 and everything else 0. And C equal to 1 and everything else 0. These comments are here. But now when it gets a little more interesting, if you set B equal to 1, or when I said B equal to 1, I messed up because B occurs in 2 places, my bad. So when I said B equal to 1, I get this. Okay, well, I think you've got the idea. What I'm suggesting is try to set each of these different letters equal to 1 and look at the vectors that come out. What I'm suggesting is the vectors that you would get would be the basis. So how many would there be? Well, you're setting A or B or C equal to 1 and D and E and F. So it looks like there are 6 vectors. So from this kind of consideration, I'm thinking the dimension of W is 6. And if you look at the example, let's see what they say. Well, they pretty much say the same thing, maybe not as in detail. they're saying, look at the matrix where I, J are that have a 1 in the ith row in the jth column. So for example, if you put a one here and a 1 here, and everything else 0, why claim that's sort of the same as this thing? So they're letting A, B, C, D, E, and F each be 1 and looking at the matrices that come out. Now, do you have to think of them as these kind of 9 tuples? No, but I think it probably helps a little bit because you know how these look. But if you want to think of them all in terms of 3 by 3 matrices, there's no problem. So when you said B equal to 1, you get something that looks like what? 1's here and 0 everywhere else. They're claiming this is a way to come up with the basis. And they're saying that when you set each of these 6 constants equal to 1 in this manner, you're going to come up with the basis. So they're saying the dimension is 6. Now that's just it in the 3 by 3 case. They're actually saying a little bit more. They're doing it in the n by n case. And in the n by n case, well, I'll either leave it to you or we can talk about it right now after class. The dimension turns out to be 1/2 n times n plus 1. Okay, so now you get the gist of what's going on. The gist of what's going on now is we already knew about subspaces, but we just learned about basis. And so since a subspace is a vector space, we're trying to figure out either of 2 forms of the question: what's the dimension of the subspace, or what does a basis for the subspace really look like? Let me see whether it's out of time. Let me see. Yeah, that's what some of the problems I gave you to do are about. So the homework was what, 1 through 9? Yeah, you already had 1 through 5, but then 6 through 9 as well. So with that homework assignment, let me just tack on, since I didn't get as far as I wanted to. Let me see. Read. Okay, read what? Read what we'll talk about on Friday, which is 2.1. If you want to get a little bit ahead, other than the reading, I can tell you probably what will be, I can tell you what will be a homework assignment for that section. So let me see. 1, 2, and 3, 8, and 9. So let me call that future homework. But I'm trying to give you a little bit of the future now. So I just said read this, and future homework would be 1, 2, 3. 1, 2, 3, 8, and 9. So I'm not really assigning this now because I didn't even talk about section 2.1. So I'd like you to read it. But if you actually read it, you might want to glance at some of the homework problems, or you might just want to wait for their next lecture. Okay. Gotta close out the class, but we have office hours, so I'll be with those who wish to stay for the office session coming up. And the other takeaway, please remember, we've got a test date now on February 4th, Friday the 4th. Okay, I'm going to have a little water and come right back. For those who can't stay, I'll see you on Friday.
Thank you, Professor.
You're welcome.
Thank you, Professor.
Very welcome. Let's see if I can open up my water bottle. There we go. Weather was sort of crazy yesterday. Any of you have snow or hail? I think some people in Pasadena did. I just had rain. Came in the evening. Okay, I'm back and ready to answer any questions. So I think the whole class was pretty much on this slide. Let me see. No, this was the new stuff. Well, maybe it was all here. Yeah, I think this was the summary, and then this was the new stuff when we started doing examples. Oh, I see. We had a question that came up from the past homework. Question 4 we did. And then I went into subspaces. So I'm happy to answer questions from the past. I'm happy to answer questions from today's lecture. And I'm even happy to answer questions from the new homework 6 through 9. I could even go here, though I'd probably prefer not because I haven't even talked about 2.1 yet. But if you need help on what's going on here, we could go there, but I think it'd make more sense to stay in chapter 1 for the moment. So any request? If there are no requests, I'll probably pick one of the problems, 6 through 9, just to get a feel for it. Okay, well, let me direct you that way. If we're going to do 6 through 9, which is in section 6, 1.6, is there any of those problems that you particularly be interested in? I'll let you look it over for a few seconds. Take a little more water. Okay, well, I'm not hearing much, but let me see. I think I have a good amount of people. Yes, I still do. So let me just pick something as just to make some forward progress here. So I'll flip the page. There, the page. Throw some lines on it, and off we go. You can still see it. Let me look at the book and see what 6 through 9 are about. So in 1.6, how about 7? Just as a starter, at least. So 7 is about what? 7 on section 6.1.6. So it gives you there 5 vectors in R3. So it gives you U1. So you're given U1 is the vector 2 minus 3, 1. U2 is 1, 4 minus 2. U3 is minus 8, 12, and minus 4. U4 137 minus 17. 137 minus 17. And U5 is minus 3 minus 5 and 8. Minus 3 minus 5 and 8. Okay, so you're given that. The vectors in this collection generate R3. So you're told that. You're given that these vectors generate R3. Find a subset of them that's a basis. Okay, a basis of what? Of R3. Okay. So the dimension of R3 is 3. The dimension of R3 is 3. So we need 3 of these vectors that would form a basis in R3. And I think the process could be just start from the first ones. There are probably many ways to do this, but certainly, what are you looking for? You're looking for 3 vectors that generate all of R3 and that are linearly independent, because that's what a basis is, right? It's a set of vectors that generate the whole vector space you're in and are linearly independent. So without thinking too hard, we could start with the first one. And suppose we consider the first one in 2. Okay, are those 2 vectors linearly independent? Well, there's only 2 vectors. Asking if they're linearly independent comes down to asking, is the 0 vector a constant times U1 plus a constant times U2? And if that's true, does that imply that A1 and A2 are both 0? If so, then these 2 vectors would be linearly independent. But you can see what this means. For only 2 vectors, this translates into saying, is A1 U1 equal to what? I can bring this one to the other side. A2 U2. So this is a question. This is a question. And if this is true, if suppose they're not linearly independent, suppose there's some non-zero constant that makes this true, then it's either A1 or A2 that's non-zero. Suppose A2 is non-zero, then U2 would be equal to what? A1 over A2 U1. So whichever one of these constants is non-zero, you can divide. And what would have to be true? The vectors, one would have to be a scalar multiple of the other. So in that sense, I could look and say, can I get this just by multiplying this? Can I get this just by multiplying this by a scalar? Well, I can multiply 2 by 1 and get this, but then when I do 2 times this, I get 8 instead of this. And so these would, what am I testing? I'm testing is U1 twice U2, and the answer is no. Now, I could worry that maybe if I go the other way, so it could be either this way or it could be what? If A1 were 0, then you'd have A2 over A1 U2 equals U1. So can you sort of what the question becomes, can you multiply U1 by a constant to get U2? We already checked the answer, no. The only constant that would work would be 2, and it doesn't work in the second position. The other thing to check is there something you can multiply this by to get this? The obvious answer would be 1/2. Would make the first components line up, but that doesn't work for the second. So what does it mean? The only solutions to this will be this. So far, what do we know? U1, U2 is a linearly independent set. You can't get one of those vectors from the other just by scalar multiplying. Okay, but we're looking for a basis. So we're looking for 3 linearly independent vectors, not 2. So maybe a sort of simple approach would be, what if we took the first 3? Maybe those are all linearly independent, and that could be our basis. So let's check. Are U1, U2, U3 linearly independent? Now, I'm trying to think if this is the best way to do this problem, but it's not a bad way from an educational point of view. It may not be the most efficient point of view. So I'll continue this approach for a little further, but I may switch gears soon. Okay, so asking are these linearly independent is the same as asking if you set this equal to the 0 vector, A1 U1 plus A2 U2 plus A3 U3, does that imply that all of these A's are 0? If so, then this is a linearly independent subcollection of the original collection. Okay. Well, you can test it out. This is A1 times U1, and U1 was this, 2 minus 3, 1, plus A2, and U2 is 1, 4 minus 2. And A3 times U3, and what was U3? I don't recall. Minus 8, 12, and minus 4. Minus 8, 12, and minus 4. Okay. So if you set that equal to the 0 vector, does that mean all the A's have to be 0? Don't know. But what is true is the first component here would be twice A1, and this would be plus A2, and this would be minus 8A3. So this would be an equation that would have to hold. The first components would have to be equal. What would be the second component? 0 would be equal to minus 3A1 plus 4A2 plus 12A3. Okay. What about the last component? 0 would have to be equal to A1 minus 2A2 minus 4A3. Okay, so if this equation is going to hold, then this would be the system that we have to solve. Perhaps the easiest thing to do, since they're all there, is start manipulating this. So call this system 1. If we multiply this thing by this equation by 2 and subtract it from the first, you'll get 0 here. 2 times this subtracted from that will give you 0 in the first equation. 2 times this and subtracting would give you, what, 5a2? 2 times this and subtracting would give you 0, right? So it appears that, make sure I did it right, 2 times the bottom equation, subtract from the first equation, gives you 0, 5a2, and 0. Okay, so that's nice. Why is that nice? Because that implies that a2 is 0. And then do something similar with the next equation. Multiply the last equation by 3 and add it to this one. So you get 0 here. If you add 3 times this to this, you'll get 0. 3 times this would be minus 6a2, and add it to this would give you minus what? 2a2. And 3 times this is minus 12, and adding it to this. Okay, so what's become clear? What's become clear is that these two equations are the same. Why? No, I guess not. I guess I'll take it back. So what am I doing? I'm adding 3 times this to this, and I'm getting 0. And now I'm getting 2 equations here that look very similar. And then I still have the last equation. Okay. So I know that a2 would be 0. And now this I could just say, what does this last equation tell me? This last equation tells me that a1 would be equal to 4a3. So what's sort of coming out of this is if I pick a3 to be 1, then a1 would be 4 and a2 is 0. And I'm coming up with a non-zero solution of this equation. Let's double check that it works. If a2 is 0 and this one is 1, I'm sorry, this one is 4 and 3 is 1. So this is 4 and this is 1. Does it all give me 0? 8 minus 8, yes. Minus 12 plus 12, yes. 4 minus 4, yes. Okay, so that means what? Are these linearly independent? No. Which really is saying that what is it really saying here? It's really saying in the end that U1 and yeah, it's saying something that I could have seen if I looked at it better. If I just take U1 and multiplying it by minus 4, I get this. So could have observed that from the beginning. This is just minus 4 times that. So that means this is already in terms of these two. So we could eliminate that. Maybe we should look at that further. Let me see. So far, what do I know? I know these two are linearly independent, and this one is just a constant times this one. Is there something fast like that that we can see in the others? Don't know. But we know the answer to this is no. Okay, so what's left to do is to check each of these. Why don't we just do that? And then I can talk about a faster way to do this later, but at least we're getting to the answer. So we have these two are linearly independent. This one is related to this one, so we don't want to include that. So let's look at U1, U2, and U4, for example. I'm just thinking though. Okay, let me check this out. If I add U1 and U2 together, what do I get? I get 5, I get 3. And this added to this would give me what? 1. And this added to this would give me -1. So if I just added these together, I wanted to see if I'm getting this, and I'm not. So, okay, I don't know. So let's check U1, U2, and U4. Are U1, U2, and U4 linearly independent? So it comes down to asking if 0, 0, 0 is A1, U1 plus A2, U2. And I guess I'll call it, why don't I call it A4, U4? Because then A4 is the coefficient that goes with U2, U4 rather. Okay. So we already did. So what is that asking? It's asking A1, and what is U1 again? U1 is 2 minus 3, 1. 2 minus 3, 1 plus A2. What is U2? U2 was 1, 4 minus 2. 1, 4 minus 2 plus A4. And U4 is what? 137 minus 17. 137 minus 17. Yeah. Okay. So if that's going to be equal to these, what does that mean coordinate-wise? 0 would be equal to 2A1 plus A2 plus A4. Setting the first components equal. Setting the second components equal minus 3A1 plus 4A2 plus 37A4. Setting the last components equal. A1. Yes, A1. And minus 2A2. And what? Minus 17A4. Okay. Make sure I did that right. A1 minus 2A2 minus 17A4. Yeah, that's fine. Okay, so this is our system this time through. Call it system 1 again. If we want, we can introduce zeros, multiply this one by 2 and subtract it from the first one. So 2 times this minus that would give you 0. 2 times this and subtract it would give you what? 5. 2 times this is minus 34 and subtract it, so that makes it plus 34, 35. I think that's correct. And do something similar for the second one, this time multiply it by 3 and add. So I'm multiplying the last equation by 3 and adding. I'm getting this by 3. That's 6 minus 6, and I add, so I get minus 2A2. And this one by 3. So what is that? 51 minus 51. 37. What is that? Minus 14. Keep me honest with the arithmetic. So I'm multiplying the last equation by 3 and adding. The first two are fine. 3 times 17 is 51. And when I do this, it looks okay. Okay. So, but look at what's going on here. These are giving you seemingly contradictions. Let's make sure of it. But so for instance, this one would imply that 5a2 is minus 35a4. And this one would imply that minus 2a2 is 14a4. But there's only two equations here and two unknowns. And this one would say that a2 is minus 35 over 5 a4, which is the same as just what, minus 7a4. And this one would also say the same thing. It would say a2 is 14 over minus 2a4, which is minus 7a4. So these two equations are really the same in disguise, I suppose. Yep. And that means that I can just keep one of them if I wish. So a2 is minus 7a4. So if a4 were 1, then a2, I just picked it to be something nice, a2 would be what? Minus 7. And that's what we have out of this. So let's see if that's true. So if this is 1, and a2 is minus 7, and I'm guessing a1 should be 0. It could be 0, but let's see what it is. So if we do a2 was minus 7 and a4 was this, oh, that would tell us what to make these things. Okay. So 2 minus 3, 1 times a1. So the first unit would be minus 7 plus 1 would be minus 6. And so for this to add up to 0, I would need a1 to be 3. So I'd have 6 here. So I think I need this to be 3. So let's check. Minus 7. Minus 7 plus 1 is minus 6. Plus 6 is 0. So that would make that work. What about the next one? 37 minus 28 is 9. And this is minus 9, so that makes that work. And then finally, the last one, minus 17 plus 14 is what? Minus 3. And 3 times this is that makes that work. Okay. So we have found non-zero coefficients, which really means what? Which means this guy the A4 can be written as linear combination of these two. So are these linearly independent? The answer is no again. Okay. So we're trying to find three linearly independent vectors so we can call it a basis. And so far, if we take U1 and U2, U1 and U2 were independent. If we try to add U3 to the collection, we got no. If we try to add U4 to the collection, we still get no. And hopefully, if we add U5 to the collection, we'll get yes. Now, this is a long way to do it, but it would work. So let's see. So what's left are, or is, the collection of U1, U2, and what's the last one? U5, linearly independent. Which is asking again, if you set this equal to this, and you write it as A1U1 plus A2U2 plus A5, I guess, U5. Does this imply that A1 is 0 and A2 is 0 and A5 is 0? Okay, do it again. U1 is again 2 minus 1, 2 minus 1, oops, 2 minus 3, 1. That's the first one. U2 is 1, 4 minus 2. 1, 4 minus 2. And this one, well, we don't need U4, we need U5. So U5, if we scroll up high enough, should be here. It's minus 3, minus 5, and 8. Minus 3, minus 5, and 8. Okay. So we're looking at A1 times 2 minus 3, 1, plus A2, 1, 4 minus 2, plus A5, minus 3, minus 5, and 8. I'm not totally familiar with A5, so I better check it. Yeah, okay, use that. Okay, so we again do the equations. So this would say that 0 is 2A1 plus A2. And this time minus 3A5. The second components would be minus 3A1 plus 4A2. And this would be minus 5A5. And then the last component would be what? This is a question mark, by the way. 0 would be equal to A1 plus 4A2 plus 8A5. Okay. Call it system 1 again. 2 times this subtracted from equation 1 would give us 0 here. And we're doing 2 times this, subtracting 2 times this is 8. Subtracting it from that would be minus 7A2. And 2 times this is 16, and subtracting it from this would be minus 19. So 2 times this, 2 times that. 16 minus. Yeah, keep me honest. This time multiply this by 3 and add it. 3 times this plus this will give you 0. 3 times this is 12 plus this gives you 16. 3 times this is 24, and when we add it to -5, we just get 19. Make sure I did that properly. 3 times this, add, yes. 3 times this, yes. 16 and 2. 3 times this, 24 minus 5 is 19. Okay. And what? The last equation still holds. This seems to be enough to give us trouble. Let's see. This would say 19A5 is equal to what? Minus 72. And this one would say 19A5 is equal to minus 16A2. So what would that mean? How could minus 7A2 equal minus 16A2? So that could only happen if A2 is 0, right? Make sure I did all that right. 19A5 is minus 7A2. 19A5 is minus 16A2. So these are equal, so these are equal. And this could only be true because if A2 is non-zero, then we get a contradiction. So what does that imply? It implies A2 is 0. Okay, so if A2 is 0, that implies A5 is 0. And if A5 is 0, then that implies A1 is 0. Okay, so it looks like we're done. Let's see. For this system to be equal, it would mean that all A1, A2, and A5 are 0, which means what? These are linearly independent. So are these independent? Yes. What was the original question? Find a subset of this that would form a basis for R3. I would say that we found it. This is it. It would be U1, U1, U2, and U5, because they're linearly independent, which means we can create any of the other vectors from these. And the vectors all span R3 by assumption. Isn't that true? Yeah, this generates R3. So using the first two and the fifth one, we can create these other, but we're given that these vectors generate the whole R3. So these two vectors and the fifth one would also generate R3. So they generate R3 and what? And they're linearly independent. So they're a basis. So our answers for a basis here would be U1, U2, and U5. Now, the only problem with this, well, let me stop. Okay, I'll say what I was going to say. It's lengthy. Okay, it's repetitive. And so the question comes up, can we do this in a quicker way? But not worrying about that, is the idea clear? We have these 5 vectors in R3 that generate all of R3. And the question is find a subset that's form a basis. We already know the dimension of R3 is 3. So it comes down to finding 3 of these that are linearly independent. We tried U1, U2, U3, it didn't work. We tried, well, U1 and U2 were independent, so that was the start. But then we tried U1, U2, U3, that was no. U1, U2, U4, that was no. And then finally U1, U2, U5, and that was bingo. That they were linearly independent, and we already knew they generated everything, so we were done. So is the method and is the solution, are there any questions on how to do this? Other than, can you do it faster? Which I think is a reasonable question. But did you follow what I did? Okay, so I guess if we're trying to do it quicker, I have to think about that. I know I needed 3 linearly independent vectors. And I had these 5 to test. You know what? I'm not positive if I could do it quicker. Maybe. Maybe I'll just, rather than think, well, let's leave that as an open question. There's an easier way to do it, perhaps. But let's turn to other questions. So now that we've done this one, which is one of your homework problems, is there another one that you might want to see in the time that we have? Have another 10, 15 minutes. Or maybe it would be best used to give you a hint rather than trying to do it all. So let's go back and look at this. We just did 9. Well, if yeah, we just did 7, right? Yeah, we just did 7. If this is discouraging because it's long, maybe 8 will even be more discouraging. So let me see if I can say anything that would be encouraging about number 8. So take a look at it. W is a subspace of R5. So it's a little different. It's about subspaces. A subspace of R5 consisting of all the vectors having coordinates that sum to 0. So I'm just checking the first one. 1, 2. Yeah, okay. So the subspace here, W, first of all, it's a subset of R5, so that you're told. But then also, you're told how it looks. It looks like coordinates, so you might as well think of them as A1, A2, and maybe we shouldn't use A's, let's use B's or something. I don't know, some other letters, because A's are usually our coefficients. So it's B1, B2, B3, B4, B5, such that what? B1 plus B2 plus B3 plus B4 plus B5 sums up to 0. That's what they said. And they're saying this is a subspace. So if you need to, if we were asked to verify that this is a subspace, what would you do? You would check that zeros in here, certainly all zeros add up to 0. You would check that if you had two vectors that look like this and you added them, that their vector addition is in there. I'm confident of that as well. And if you multiplied by a scalar, that is closed under scalar multiplication. So it's not hard to verify from what we did earlier that this is a subspace. Find the subset of this that is the subset of the U's. And they give you 8 different U's. Okay. I'm not sure I want to write them all out, but the U1 up to what? U8. And they want a subset of this that's a basis for W. Okay. So this is different than the previous problem, definitely. Has some similarity. So you want a subset of this collection that is a basis for W. Now, what do you know from what we did today? You know, W is a subset of this. W is a vector space, so we know that the dimension of W would be less than or equal to the dimension of R5. And the dimension of R5 is 5. So what we need is we know this thing has dimension 5 or less because it's a subset of this. And now the question is, can you figure out what the dimension is, and can you find what a basis would look like? And let me make sure that's what they're asking. I think they're asking for an actual basis. Find the subset of the U's that is a basis. Okay. Well, but my question first is, do we know the dimension? Do we know that the dimension of W? Well, we know it's 5 or less. So and we know that okay, so we're trying to create a basis from this. Okay, so now it's become clear to me what we're trying to do. The basis for W will have 5 or fewer vectors in it than U1 through U8. So we have to throw out the ones that can be created from the remaining ones, okay? It's not clear to me yet what here's a different question. Can you find any basis for this? I'm thinking, okay, yeah, so there's 2 questions. Can you find a subset of this that's a basis for W? That's their question. My question is, can you find the dimension of W? Because that would be useful. If we knew the dimension of W, then we'd know how many of these we have to throw out and how many we have to keep. So for example, suppose I knew the dimension of W was 4. Then I would have to find 4 of these that can be created from the other 4, and then just eliminate the ones that are duplicates, which is sort of along the lines of what we did in the previous problem. So now it's beginning to dovetail into the previous problem. The previous problem, we had these 5 vectors in R3, and we knew we were trying to get a basis for R3, so we knew we had to throw out some that we could create from the others. We ended up throwing out these 2.
and keeping U1, U2, and U3 because they were linearly independent, and we can create these two from these three. So the question now, two questions. What is the dimension of this space W? And then which vectors in here can you throw away and just keep that dimension number for the rest? So what do you think? Do we know, this may be an easier question. Do we know the dimension of W? Well,